Hello, everyone. Hi, Amanda. Hi, Aaron. Thanks for joining. Hello, phone number. I can't see who exactly you are. Hi, Tom. Thanks for joining. Really excited about everything that we're going to learn in the next 72 hours, the next whatever 72 hours is plus 24 hours. However many hours you have before your exam, we're going to make every minute count. Hello, Madeline. Thanks for joining. I'm going to be here personally answering all of your questions. I've taken some time off of my other responsibilities, so this next week I will just be able to answer any questions on the online form, make any revisions. I'll even look at your grades. If you have like some questions that you've answered, but you're not sure how it would be graded, I can look at some feedback, give you another set of eyes so that you'll know exactly what you're looking for when you're aiming for the exam. In the chat, someone give me a thumbs up if you can hear me okay. Just testing this out. We're going to have an interactive chat. We're going to have our panelists once they join in a few minutes. Thumbs up. There we go. Thank you, Aaron. And then yeah, we're gonna just open up the floor and you'll be able to ask me questions in the chat. I just want to say, this is a really difficult exam. I did only, when I passed this exam, I was studying every single day. I canceled everything. I just locked myself in a box and turned off internet in my apartment. Just worked on studying as I was also doing PA and exam STAM at the same time, which was crazy. I wouldn't do that again in a million years. But you can definitely give yourself an advantage, just by being here. The fact that you showed up here on a Saturday, you took time out of your busy week, shows that you are prioritizing studying above everything else. So that gives you an advantage. This is a competitive exam. The SOA doesn't really say that, but you are competing against other people who are taking this exam because everything's graded on a relative basis. So the fact that you're already here shows that you're in the top 10%, the top 5% of people. Hi, Ahmed. Thanks for joining. There's So while we're waiting and we have everyone here, we're going to go ahead and let go on our poll. Our first poll is just about your background. Have you taken exam PA before? There's absolutely no shame in having to retake PA. I understand that you're prioritizing other things in your lives besides just taking exams. And if you have taken it before, that gives you really an advantage. If you haven't, then that's great. That means you're already working really hard. You're going to pass on your first attempt. I believe it. So we see here, I see most people have taken PA before so far, 75%. That's surprising. Most people are in health insurance, life insurance, savings and retirement. So we don't have any property and casualty actuaries, which makes sense. We do have a lot of health actuaries. That's fantastic. I actually am a health actuary myself. That's my background for Milliman, working with like healthcare providers, like your big health plans, doing consulting, and also savings and retirement. That's actually interesting. I think like pensions are sort of underrepresented, but there's a lot of low-hanging fruit when it comes to analytics, because that's like an older industry that has more room for innovation. How many exams do you need to get your ASA? Yes, 80% just need exam PA. So that means once you pass this exam, you're going to be home free. You're going to be done, and assuming that, yeah, once you walk out of that prometric room, you can start playing, victory music, knowing that you passed and you're getting your ASA, you're getting that raise, whatever it is for you. If it's like $5,000 or $10,000 or $15,000, that's great. And then some other people, 20% need PA, the modules, fundamentals of actuarial practice, and one exam. So that's actually where I'm at. I actually need to do exam LTAM and the modules. So I can empathize with all of you as well. We're almost there. Keep going. So yeah, Dave Snell, ASA, MAAA, and a lot of other letters after his name that I can't even pronounce. He's a technology evangelist. Dave and I first met when we were at the Predictive Analytics conference in Philadelphia in 2019. His specialty is working with machine learning, and he teaches at Maryville University. He's also a lifelong editor of the Society of Actuaries Predictive Analytics and Futurism newsletter. And he's worked with insurance, financial services, helping to leverage their expertise by introducing and inventing creative technology-based tools to help them overcome obstacles that limit their potential. And then we have two data scientists from an AI consulting group working on the bleeding edge of technology using predictive analytics in real life. Ahmed Rasheed, he works in, he's an ML engineer at Revolve AI. His master's is in electrical engineering, and he develops complex 3D computer vision systems leveraging visual data on a very large scale. He's designed and developed a robust object tracking library for Revolve AI, developed multiple camera analysis systems for human pose tracking. So, all those videos you see of AI and video, that's what he's working on. So without further ado, Dave, why don't you take over?
Okay. Let's see here. Post disabled.
You can now screen share.
Okay, let me get to my. Okay. And it says I'm screen sharing, but I don't see anything here.
I see it.
Okay, there. Okay, first, thanks for letting me talk about machine learning. It's a complete game changer for the way actuaries will do business. And why do you want to listen to this from an old guy like me? It's because I love this stuff. I've been involved in it for 4 decades now. I want to share the excitement about AI and why it took until now to become important, and a few techniques that you ought to become familiar with. First commercial hard drive cost over $3,000 a month to rent. That's rent, not buy. And it held 3.5 megabytes. Now data storage is cheap and easy. All of you have heard that you have more computing power in your smartphone than NASA had on the first moon landing. But did you know you have 1 million times more of the power? The onboard computer on that flight was 4K. And note here that the cost per gigabyte in 1979 was over $18 million, and now it's under 2 cents. I'm going to talk very fast, go through a ton of slides on here, but you'll get copies of all the slide images. So just kick back, enjoy, and think about what you want to ask at the Q&A. Data is now available, but as you can see, insurance companies just have not been in the loop on this until very, very recently. But gamers have. 20 years ago in 1997, let's see here. Okay, IBM's Deep Blue beat Garry Kasparov, the world champion in chess, but people claimed it could never understand human language. But then in 2011, Jeopardy was beaten by Watson, and it even handled the pun on words in Jeopardy. As you probably know, Go is more complex than chess. At any given point in time, a chess player may have about 20 moves. The Go player can have about 200 available moves. Lise Hodell's been called the greatest Go player who ever lived, but the AlphaGo program beat him almost 4 years ago now, or actually over 4 years ago. I've heard of the ability to play just by watching a game, but learning to produce the game code just by watching is really new and fascinating. This was done after watching a 2-minute segment. These achievements were impressive, but this is dramatic. This is really dramatic now. Let's consider what happened here. Unencumbered by the baggage of human knowledge, the AI machine learning program AlphaGo 0 was able to learn faster and reach a much higher level of expertise. That means there was no training of previous human games here. All they did was take 2 instances of the program, they fed them the rules of the game, and the instances played against each other. In 72 hours, it was able to beat the best person in the world. Lost my screen. Here we go. Okay, Sophia, the robot's been granted citizenship in Saudi Arabia, and she's a common talk show guest. A lot of smoke and mirrors there, but it's still very impressive. Xiao Yi did not just pass the Chinese medical exam, it got a very high score on it too. Go took 42 hours to master, but chess mastery took only 4 hours because it was so much easier for AlphaZero. Here's a milestone, because to win at poker, you have to figure out when your opponents are bluffing, and sometimes you have to bluff. And this went against 6 human experts in poker. Okay, here's an app from MIT, which is really cool because it means that from 1,000 miles away, you can cough into a smartphone, and this will determine whether you have asymptomatic COVID-19. Up to now, I've been talking about AI and machine learning, but what is it? You know, if you're a fan of Princess Bride, you know, you'd feel like Inigo Montoya there. You know, what is this word and what do you think it means? Well, basically, machine learning seems like magic to some, but it's not. It's really, really easy. And I got to show you what's behind the curtain here. In traditional computer science, we hard code our logic and we apply it to data in order to create output. Where's my cursor? Okay. With machine learning, though, we take sample data and the output from that, and from that, we infer what the logic of the program should be. And this is supervised learning, but that's all it is. That's it in a nutshell. Okay, there's always a religious war over which IT programming language is the best one for a circumstance, but regression analysis and statistical data analysis, R seems much nicer. Python is much more common in Silicon Valley for machine learning. The SOA is great for looking at where the puck used to be, but for this exam, stick with R, but then use other languages afterwards, or at least explore some of the other languages afterwards, particularly Python. Frequent item sets. This enables underwriters to infer that if you've taken albuterol and guaifenesin, then you almost certainly take ipratropium bromide, whether or not you reveal this on your insurance application. And it can serve as a kind of red flag to alert that the applicant is not being truthful, or that some drugs are being prescribed off the grid or by some other doctor who may be worth contacting. Netflix does the same type of thing to determine what movies to recommend to you. No one person has seen all the movies, and no movie has been seen by all the subscribers, but by looking at these clumps in a very sparse matrix, we can infer movies you'd like to see based on other movies you liked and based on movies liked by people who like similar things to your preferences. Amazon does the same thing with purchases, and as you see, it does a very good job of suggesting items that you might wish to buy, even though you never even knew about them. Throughout the bulk of human history, we've lived in fear of famine, plagues, and war. Those were the 3 big killers of humankind. But in 2012, about 56 million people died throughout the world. 620,000 of them died due to human violence. That's war killed 120,000, crime killed another 500,000. In contrast, 800,000 committed suicide and 1.5 million died of diabetes. Sugar is now more dangerous than gunpowder. How might this impact the sale of insurance, or even how we live our lives? What would people act like if there was no likelihood of heaven or hell because you might not die? What if we have the ability to be like the Highlander in the TV series? Okay, the Truman Show was just the beginning, and now we're heading towards knowing our genome, our microbiome, and all the other ohms, what Dr. Eric Topol calls the panomic perspectives. Here's another great book about the future of healthcare, although it may scare you. Who here can tell us the main criteria for life insurance rating in the 1950s? Well, I'll tell you ahead of time. They were age, race, and gender. Age is still important. The other two are not even allowed in many countries. Smoking and credit scores are now very important. A credit score might be even more important than smoking status. When you develop a product for one market successfully, though, do not assume that the rest of the world will all automatically like it. Cultural differences make a big factor in whether your model will be accepted, whether your product will be accepted. Most of you probably remember the Target debacle with predictive modeling. It was highlighted in Forbes in 2012. They were able to predict a teenager was pregnant even before her own family, especially her father, knew about it. But the public reaction was, ooh, you know, data stalkers. Now, probably everyone knows that Progressive was the first car insurance company to really capitalize on predictive modeling, and they soared from about a 2% market share to over 8% in a couple of years, but their profit margin was way, way better than everyone else. They were able to be more competitive on cases that they wanted and to lose cases that were unprofitable. They had a great idea there. They would splash the market with ads saying, you know, we care so much about you, we will shop for you. And so Ahmed comes in and they say, oh, it doesn't drive after midnight, doesn't have any DUIs, really good guy. We'll give him a great rate. He will come away saying, Progressive, that's a great company. They really treated me well. Dave comes in, they might go out to the website and see a picture of him, standing by a keg, with a bra on his head, talking about how his muscle car is the fastest one off the line. And Flo comes over and goes, oh, Dave, I'd really love to have your business, but I got to be honest with you. Allstate and State Farm, they have a better rate for you. Really wish we could have got your business. Wouldn't it be great if you could send all the bad cases to your competitors and keep the good ones for yourself? Behavioral science is kind of the secret sauce to be able to do that. Here are some examples of how we used predictive modeling in RGA when I was there, but I'm going to really flash through these things. You can read them afterwards. The one I really want to pay attention to is claim fraud detection, because here predictive modeling was used to do what you do so often, determine the break-even point for the protective value of medical requirements, but also to go ahead, and find all the cases where if they put a claim in, you got to really investigate that claim. That's off to the right group here. But also important was the cases where these people are so honest, if they put in a claim, don't even bother to investigate that. Save the money, save the time, build up the goodwill. That's another benefit of predictive modeling. The long-term capital management company involved two incredibly brilliant quants, Myron Scholes and Robert Merton. You've heard of the Black-Scholes formula. That was Myron. They got full of themselves. They thought that their diversity across the world was going to save them. It didn't, because there was a contagion factor where if something goes wrong, or something went wrong in Japan, that spread over to China, that spread to Russia, that spread to Europe, that spread to the US. The result was a huge multi-billion-dollar bailout. So you have to consider these factors in your models. When is a $6 billion more important than $30 billion? When your company goes into receivership because it can't come up with the $6 billion in 7 days. And that happened to a company that I worked for, General American Life. They had a provision in the contract that said you had 7 days to get your money back. It was basically a gift that was bought by pension managers, and they are bound by very strict rules as to what assets they can hold. When the Moody rating of the company went down by 1 point, it became a threshold. There was a run on the bank. The $30 billion company went into receivership. How many companies do you know that could come up with 20% of their assets, even Apple or Microsoft, in 7 days? None of them, really. So you have to consider the other factors besides your numbers when you're going into your modeling. All right, what if all your pictures could be scanned for the use of tobacco? Your cable company revealed whether you have the premium couch potato package. Your wrist monitor was streaming vitals by the minute wirelessly, and your fridge was reporting on your food purchases, and your shoes relayed how much you walk, and your clothes were all gathering info and sending it along. What if the prescription pill you take has an embedded nanochip that travels through your bloodstream and sends signals to your smartphone? Oh, it goes on and on and on. But this is what's happening. It's a new world there, and we have to get ready to embrace that new world. Euclidean distance examples. That's simple in 2 dimensions. We all know that a squared plus b squared equals c squared, and that's really cool. But the cool thing is that it works in higher dimensions too. So we can go ahead and figure this out. And once we do that, we can apply this to higher dimensions. But there's a danger when you do that. When you're applying stuff to higher dimensions, you have to realize you're only looking at one perspective on there. If we look at Orion up in the sky, it looks like Mesa is very close to Bellatrix. Actually, we are 4 times closer to Bellatrix than Mesa is, because we can't look from the side there. We can't see that other dimension. And when you take your data clumps and you show them in 2 dimensions, or even 3 dimensions sometimes, what you're seeing is often a very misleading picture of what the data actually looks like. It's very difficult for us to accurately comprehend data beyond 2 or 3 dimensions. It may look like it's okay on a 3-dimensional plot, but it's not when you actually see it from other perspectives on there. So be very careful about that. Michael Murphy has some great links out there for anamorphisms, where you see some impossible looking sculptures. All right, Euclidean distance. I said it could be extended to any number of dimensions. Here's a simple 11-dimensional variable situation. We have 2 points in 11 dimensions, and the distance from point 1 to point 2 is going to be the square root of 1 minus 0 squared, 3 minus 3 squared, 0 minus 5 squared, 2 minus 0 squared, on like that there. So we can actually come up with a number. We can come up with a distance number. When you're doing the clustering, the number can't be negative. It has to be 0 if you're going from a point to itself, and it has to be symmetric. If you're going from A to B, the distance is the same as from B to A. But given these rules, you can choose any number of different metrics for distance. And there are lots of different metrics that you can choose for distance. Euclidean's the most common, but it's not always the most appropriate. Why would you normalize your data? Our sense of normalization is to keep one parameter from overwhelming all the others there. Typical example from Amazon is the square footage of a house. You don't want that to be treated exactly the same as the number of bathrooms. Maybe bathrooms are important to people. They are to me, I know. But square footage would overwhelm those if you don't normalize the data first. Okay, why do we care about data classification? It gives us some appropriate ways to normalize that data there. Zip code might be nominal, as suggested in most texts. It might be ordinal if it's transformed to relative cost locations. You know, zip code 62002 in Alton, where the median price is about 80K, it's going to be a lot less expensive than the zip code 90210 in Beverly Hills. Quantitative observations. Box and whisker plots and violin plots are often helpful in the analysis of raw data and the choice of how to normalize it. N-1 encoding is generally better than the 1 of n encoding because it avoids the inherent collinearity in 1 of n. It's easy to go through and see that. All right, if we have that 11-dimensional case again, and we normalize our data and we change the non-numeric variables into numeric variables, what we've done is we've expanded the dimensions tremendously. And so here's that same case again, but now we have 72 minus 65 squared, 203 minus 128 squared, on like that. But notice what's wrong with this picture. We also have 70,000 minus 95,000 squared, okay? That's 25,000 squared. That's 625 million. Nothing else matters if you have that in your parameters there and you haven't normalized first. Clustering. Oops, excuse me. Clustering separates your data into groups that are more alike. One of these things is not like the others. You know, you all saw it on Sesame Street as a kid. Clustering is almost always the first step towards classification. It doesn't automatically put labels on, but when you look at the clusters, then you can often apply those labels. We do this in insurance with the body mass index. Okay, the most common clustering method is k-means, but it's not always the most appropriate method. When you have a physical exam, a BMI of 30.0001 categorizes you as obese, while a BMI of 29.99999 is just considered overweight. But a person with a BMI of 30.001 is probably not that much more of a weight risk than a person of 29.999. So the world is fuzzy and there's a lot of overlap, and we need to consider that in our pricing, that this person is partly overweight and partly obese on there, rather than these crisp decisions. At the airport, clustering techniques are used as part of the TSA screening for terrorists. Not whether you're a dog or a cat, but whether you're a terrorist or a innocent person. Okay, here's one of the reasons why k-means clustering is so common. It's simple to understand, it's easy to run in code, it's easily scalable, but you have to specify the number of clusters k ahead of time. And you can do that by basically, well, first you pick k random points to be the cluster centers, and you keep assigning each point to the nearest cluster, and you recalculate until the points stop moving from one cluster to another. Let's see here. On k-means clustering, here's the process there for each of the green dots. Sum the x values, sum the y values, compute the average, and it's a simple process. Here I show this visually as you're going through to create. Note that this depends on your initial assumptions. It also assumes that your clusters are going to be kind of spherical in nature. Here I made it a little bit easier to see those, so you don't have to keep watching like that. All right, the lowest mean squared error. If you have 1,000 observations, the lowest mean squared error would be k equals 1,000, because that means that every point will be in its own cluster. There's no error there. The highest would be 1. Okay, those are easy answers, but they're useless for us. We really want a number somewhere between 1 and 1,000 there. So how do we do that? One way is with an elbow curve. With the elbow curve, you track the number of clusters versus the errors obtained on that, and you look for something like an elbow. If you're lucky, you see something like that. Another way to approach this is with a silhouette curve or silhouette analysis, which can be used to study the separation distance between your particular point there and the nearest clusters nearby. If it's 1, that's perfect. If it's -1, you just classify that one incorrectly. K-means alternatives. Things like spectral clustering and others might be more appropriate depending on your data distribution. There are lots of alternatives to k-means. A Gaussian mixture might be a better fit for some situations. Here's a website that you can go to that shows you lots of different distributions and what would happen under the different clustering techniques there, how well that would fit the various distributions. I like hierarchical clustering a lot. I really like that, but one reason is it's easier for non-mathematicians to visualize, and you can take a whole lot of dimensions there and get not only which ones are closest to each other as far as clustering, but get an idea of how far apart they are too. And that becomes very important. I've written an article on hierarchical clustering, and you can see that there too. I'll give you 4 quick slides on how to do hierarchical clustering in R, and you can go through those after. Now let's jump to neural networks. Neural networks, artificial neural networks are really, really cool. That's because real neural networks are really, really cool. Real neural networks, the one that I'm holding there is an actual human brain. It's been colorized. That flap that you see on there is the meninges. If that's infected, you can get meningitis, but we all have about 86 billion neurons, maybe some people less than others. You probably know some of those people, but they have tons of connections involved. Here's a very oversimplified picture of a neuron, grossly oversimplified. Typically, you'd have around 10,000 different dendrites or inputs coming into that soma there. The axon could be as short as a couple millimeters if you're going from one neuron in the brain to another, or it could be as long as a few feet if you're going from the base of your spine to your big toe there. At the end of that, you have these terminal buttons that allow you to have jumps or synapses, the gaps to other neurons dendrites there, and we have hundreds of trillions of these things, and there's all kinds of feedback loops. And it's not just electrical, it's also chemical for the calcium and phosphorus and other ions in the mix. What's an artificial neural network in the context of machine learning? It's just a metaphor where we use the biological neuron as a metaphor for the artificial neural network. It's so much simpler by all measures. Okay, all we have is we have a bunch of input. Our weights are going to be the counterpart of the synapses there. That's what you have to go through to get to the soma. And once you do that, once you've done your summation there, then you want to use some sort of activation function to transform that. You could think of it something like normalization there. So you transform that, and then you have your output coming from that. Activation functions can take many forms. They used to start out in the old days as a threshold function. That was not very flexible and didn't have a derivative at important points here. So the sigmoid was chosen because it had 0 to 1 as a nice range that it would compress everything to, and it was differentiable. If you wanted -1 to +1, you'd use hyperbolic tangent. But those have been pretty much cast aside in the deep neural networks now by the ReLU, the rectifier function, or the leaky ReLU for the GANs. Okay, Perceptron. It was the beginning of this whole thing, but it couldn't do anything like an XOR function, which is very simple because it didn't have any hidden layers. Once you add the hidden layers, you add a lot of power to your artificial neural network. Again, it's a simple concept. You have your inputs, your hidden layers, and your output. How does this work? Well, you start out with your weights or your synapses. You randomly initialize those to small numbers, but not to 0. Forward propagate that vector of the first observation, you get your predicted results there, the y hat. Each feature goes into one node of the input layer. You compare your y hat to the actual volume, actual values that you want, and you get a cost function. Once you have that cost function, you say, okay, how can I reduce that cost function? What part of the cost function was attributable to this weight over here? What to this one, unlike that, and you work backwards there. That's called back propagation. Okay, when you're doing this, gradient descent is a nice method, but often gets you in a local minimum. So stochastic gradient descent is often used to test several bands at once within the range, and that will often get you to a global minimum rather than a local one.
Dave, I have to cut you off here. We're going to switch over to the Q&A.
Okay.
We've been collecting questions from the chat, so we'll go back through our through some of your older slides and dig into these. What we're really trying to do is pick your brain on predictive analytics so that everyone here can use this as ammunition when they have to write their answers. They'll be able to write very persuasive, eye-catching descriptions like you've done with these slides. The first question was from the target example when you talk about data privacy. And in our exam, we had the diabetes exam. I think it was from June 16th, 2020, when basically you're using a model to predict if a person, I think you're predicting a person's cost, and there's a race variable that you're using. And the question is, should you be including that race variable in the model? Sometimes that could be appropriate if it's in a medical context. Maybe that's related to their genetic predisposition for certain diseases. Otherwise, it could be completely off limits, and that would result in a racist model, which we want to avoid at all costs. So assuming that we have some variables and we want to anonymize the result, but still use the input in the model, how can we protect people's privacy so that we don't have a scandal like what happened with Target?
Okay, that's a very good question, and it brings up the ethical issues in modeling there. Obviously, we all discriminate for all kinds of things. I see Ahmed has a different skin coloring from me. That's cool, but if I were to use that unfairly to discriminate in insurance or something like that, that's not cool. So what we want to do is to look at the context that we're using these discriminators and say, is this a valid context? is this an ethical context? What I like to say is it real? Is it relevant? Is it ethical? Is it accessible and easily usable? And is it legal? REAL. Is it a real parameter there? And if so, then we can use it in that context. If it's not, then we should not use it in that context. Does that help?
Yeah, REAL. What did that stand for again?
That's relevant, ethical, accessible, and legal. And what's legal and what's ethical may not be the same.
Second question is talking about the importance of always considering the business context. In your case, you talked about like $6 billion being more important than $30 billion. What are some other insurance examples of when you might choose a model that has worse predictive power? Like, let's say a linear regression model or generalized linear model, as opposed to like, a random forest or, that has like higher predictive power. What are some of the, business considerations that actuaries need to think about?
Look at your client. If the client doesn't like that newfangled stuff, she or he is not going to believe what's coming out of that neural network, which lacks transparency, or even the random forest, which is a little tough to follow. In those cases, what you might rely on is either a linear type regression or even a decision tree. The decision tree has some fantastic qualities to it. One being that you don't have to normalize the data. You can actually show the actual values that the client's familiar with, and outliers don't matter either. So all of these things can be taken into account. And I have a slide on that later that shows normalized values of the decision tree, which are kind of, geeky versus actual values on there where the person can say, oh yeah, I understand that color is blue and this person has a Toyota 1989 or something like that, Celica on like that, then I can do this. Whereas if it's translated into a number from 0 to 1, it doesn't have that much meaning to the client. So you want to relate to what does the client understand? What's the sophistication level of that person? What do they want to see? Show them what they want to, or show them the results that you want to show them in the format that they want to see.
Great answer. I hope everyone's taking notes. I certainly am. In the cursive dimensionality example, where you talk about the, the stars example, where you're looking at like a two-dimensional projection of 3 dimensions of data and how you're losing information in the context of k-means clustering, where you're using, Euclidean distance. How does the cursive dimensionality apply to other types of models, like regularized regression or random forest decision tree? And what can we do in order to, reduce the effects of that?
Okay, one thing you could do is principal component analysis. But before we jump into the answer, let's address the question a little bit more too, because actuaries have a tendency to say more data is always better. But more data is not always better. The more parameters you have, the more you suffer from the potential for the cursive dimensionality. And what can happen, I do have an example later where I show with a simple Excel workbook that if I add a new variable to the mix, it will increase my R squared. Anything that I add there will increase the R squared, but I just put in a random numbers in that variable. What's more important than the R squared there is the adjusted R squared, which penalizes you for the extraneous or extra parameters that you're adding. So focus more on adjusted R squared than regular R squared. But also, if you have a lot of variables that seem to be somewhat similar in nature, say you have latitude and longitude, but you also have the city and you have the county, you have the type of building and stuff like that, all this geolocation stuff, it might be important, but it's probably only important as one parameter, because if you introduce all of these things, you're introducing collinearity, and collinearity will really screw up your models. It's a bad thing. So the more you know about your data, the better. And even though you're an actuary, and even though you're an expert on calculations and stuff like that, you're probably not the expert on this data. So seek out a subject matter expert and try to show your results to that person and have that person say, oh yeah, I understand. Well, that's a really unimportant one. That's a really important one. And pay attention to what that subject matter expert is saying. Okay?
Yeah, great question. I'm going to ask this one to Ahmed. Amanda asks, what are your thoughts on normalization versus removing variables versus transforming variables in your data?
Well, it's not necessarily that one is bad and another one is good.
I want to hear from Ahmed, Dave.
Oh, sorry.
You're good.
It's okay. Normalization is basically dividing the data limits. Like it's if there are huge numbers in the data set, we basically normalize to 0 to 1 or -1 to 1, some limitized data. But if we talk about transformation, it changes the data. The actual data, if we have some non-linear data and we want to convert it to a somewhat linear data, we apply some transformation, or this changes the transformation actually changes the domain of the data. Like we have different transformations like Fourier transformation, Gaussian transformations. They actually change the data, but normalization keeps the data intact but changes its limits. And while removing the data from removing some of the features, actually reduce the dimensionality. If we have huge number of features and we want to remove few of them which are not useful, and we know those features are not useful, then we can just eliminate those features in training our models or predicting analysis. So I think these are the basic differences in these three techniques. David would also emphasize more on this point, I guess.
Dave, one of your slides talks about simplifying the problem. In insurance, you often will predict something like claims, and then you'll simplify it down to like risk class, like preferred plus, where like preferred is like the best risks or the healthiest people, and then preferred plus, and then you just have like declined, like people who you don't want to cover at all. So you're taking like a numeric, like a regression problem where you're predicting a number and you're turning it into like these simple labels. Why do actuaries do that? Why don't we just give our underwriters numbers? Why don't we just tell them this is your predicted claim cost, $50,000 per year?
First off, people are not very good at numbers. Actuaries are maybe an exception, but even actuaries are not very good at numbers. The human brain is not tuned toward these. For millions of years, or at least thousands, depending on what you believe. People were running through the forest, and the important thing to them was, oh, there's a lion in the bush there. That lion might eat me. It doesn't matter whether there's 1 lion or 17 lions, but there's a danger there, and I see that pattern. If you can show underwriters a pattern, they can relate to that. If you can show any people a pattern, they can relate to that. And I have other slides that actually test people on pattern recognition. I show you 20 images. One was that Tasmanian devil that you saw short earlier, but with seeing each one of those images for 3 seconds, and then I would test people to say which of the images have you seen before, which ones have you not, and invariably out of the 20 images, people get 19 or 20. We are fantastic at patterns, and underwriters are too. Underwriters can say, yes, this person had a quadruple bypass last year. Buddy's on statins to control that. He's got diabetes, but he's keeping the A1C down. He's had this problem in the past. Oh, but he's kind to his mother. All of these things, they look at it holistically, and a pattern emerges out of there. That's what underwriters really want. That's what they care about. That's what your client cares about. They don't care about numbers, just numbers. Okay.
You heard it here first. Be kind to your mother and you'll get discounts on your insurance. Aaron asks, I'm having a difficult time understanding how to use the results of a clustering in model. With PCA, those can be added to the model instead of the variables that make up the PCA. With clustering, is there something we're supposed to do or could do with the clusters, if that makes sense? And Dave or Ahmed, if you think that you have a good answer, you feel you can both answer this question if you want to.
Okay. Let me jump in and then you correct it. When you don't know much about your data, when you just get a big clump of data and you don't know what to do with it, clustering is a great thing to do first, because now you can look at those clusters and or take those to a subject matter expert and say, do they make any sense to you? And the person looks at that and says, oh yeah, those are the people who aren't very good at this. These are the people who are very good at that. These are the ones you got to be careful. Oh, those are crooks. These are the ones who are much better. So they can put labels on those clusters, and now you have more meaningful data. Ahmed, sorry, let you jump in. I think you're muted.
You're muted. We can't hear you, Ahmed. Your microphone's not working.
Sorry. I'm really sorry. They've actually explained it pretty well. Clustering actually gives meaning to data. Like if we don't know anything, if we don't even know the target variables, then we can cluster the input data we have into multiple sections. Like David explains, we can use to find the best cluster fit, algo methods, silhouette methods. So we can actually give meaning to our data. That's the best clustering that can do. And about PCA, that question also at PCA, net PCA is mostly used for which I know is dimensionality reduction, like feature reduction. We have huge data, we can break down into small number of features and train our model on that. So it also helps to extract meaning out of data if we don't know much about the features we have.
Absolutely. So what you said in the beginning is when you just get a big clump of data and you don't know what to do with it, and that's because it's unsupervised. Like supervised learning means you have a target and you want to optimize something, but when you don't have a target, you just want to see how do these people compare to each other. You can use that. Great. Well, thank you so much. We didn't get to all of our questions because we did have a lot of them, but I will go through the chat afterwards and send out answers to them. Now we're going to switch over to the exam prep phase. So this is more talking about how everyone here can take their exam. What can you do? How can you apply this knowledge in order to get a maximum score? We already shared. I just shared with you the results of the Zoom poll, so you could see, other people in this class. So one of the best things that you can do for yourself is to plan out the rest of your study time. Now that after you get off this call, you're going to be really hyped up. You're going to be really excited. And so you want to write down what you need to do and then when you're going to do it. So, today's Saturday. So you have Sunday, Monday, Tuesday, Wednesday, and then your exam. So try to take a practice exam every single day, 5 hours. Don't use any notes, use a single monitor. Be honest about, what you know, and then go through and then grade it. Once you've kind of taken a break and you can come back and look at your stuff objectively, then, just repeat that again. Take rest time between them. Don't grind out 8 hours in a day and then just take the whole next day off. It's much better if you have some routine. Also, personal tip is to study at the same time that you're going to take the exam. So if your exam's scheduled at 12 p.m., start studying now so that you'll have the routine going. And then when you walk into the exam center, it'll just be like another day. Get lots of sleep, of course. That's when your brain stores information into your long-term memory. And then personal recommendation is the day before the exam, take a rest day. Do some practice, do some review, but don't burn your brain cells. Give yourself rest, go bowling, go watch a movie, go for a hike, hang out with friends. just make sure that you're really relaxed so that you can get a lot of sleep. And then on the day of the exam, do be careful about how much fluid you're drinking, because this is a 5-hour, 15-minute test. And when you include like the time that you check into Prometric and, you know, do all that other stuff, it's actually longer. It's more like 5.5 hours. And then after, you know, plan your celebration. What are you going to do when you pass? You know, text your friends now, get a booking at a restaurant, or do something so that you have a really clear objective. So you can say, okay, I'm just going to go into a cave and just focus on PA stuff for the next 4 days. And then I'll come out and I'll pass and I'll be excited and I'll have my ASA or be closer. And so this is really a modeling exam. So here are the word counts for all 8 of the solutions. These are the model solutions from the SOA. And I put these into a word counter. And the first word is model. That has the highest frequency, 232 occurrences. And the second is data. And then, of course, you see age variables and so forth. So, you know, if you're thinking, oh, I'm going to get a passing grade because I'm just going to focus on the exploratory graphs, I'm just going to make really pretty graphics, or I'm just going to master the writing sections. No, you're not going to pass unless you understand the modeling, because that's the core of the exam. And here's some of, so let's try to forecast what topics are going to appear on this exam. We could fit a decision tree model to this data, but I think just by looking at the tables, we can extrapolate. So if we looked back at all of our old exams going back, you know, we're up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sittings of PA. In the past, they would give like different exams for each day. But in this sitting, they've already announced that there's just going to be one exam. I think that is to help make the grading more consistent. So, you know, generalized linear models always appear. So you can guess well that there's going to be a GLM on this exam. Stepwise selection hasn't appeared in a few sittings. So I would definitely review that. Elastic net and ridge and decision trees. You know, Dave talked about the importance of decision trees and how they're really useful. Elastic net and ridge, those have actually been tested a lot recently. So I would actually focus more on random forest and GBM questions, because those have not appeared very often. Now, that's just my own personal opinion. If you can come up with your own hypothesis as to which questions you think are likely. And then for unsupervised topics, you know, correlation, k-means, hierarchical clustering, PCA. We haven't seen a k-means or hierarchical clustering question in a long time. In our exam, like our custom exam, the Titanic exam and the health cost practice exam, as well as the apartment applicants exam, we have some questions that relate to, you know, k-means and hierarchical clustering. So yeah, expect something like that, and also PCA. So of course there have been some format changes to this sitting of the exam. The SOA is making it, you know, I think they want to, I can't speak for what they want to do, but here's what they're doing. They changed the tasks and instructions. So now they're incorporating business context into the specific tasks. So in the past, it might just say, you know, fit a GLM and select which variables you want. Now it will say, you know, your sales manager, you know, has told you that these 5 variables need to be used by their sales team. Now fit a GLM that incorporates these 5 variables. You know, so you're not just going to be making choices based on the statistics, but you're also going to have to consider the business case. So really read carefully. And the communications elements. So the old executive summary format was, we're going to take all of the writing and we're going to group it down on the very last question of the test. And that's going to be worth 20 points. And the problem with that was that people would get stuck in the earlier tasks. They would get to the end, they would run out of time, and then they wouldn't get a good score. So now they're breaking that up. So they're not changing the syllabus at all. but they're taking that big glob of writing at the bottom and they're spreading it out. So you really need to be, just read when you see, explain to a non-technical audience. That's the key word. Or explain using simple language. That means that you have to go into like sales mode or, writing mode where you're not talking to actuaries. Imagine that you're talking to, an HR person or an underwriter, or someone who works for your company that's not an actuary or a data scientist. And also writing and executing code in RStudio. So they do expect you to know more about R now. You do need to write some code from scratch for these basic things. And these aren't really new. If you look back through the SOA modules, you look at our sample exams, we're already doing this. So when you do your practice exams, don't be afraid to try making some changes to the code yourself. Look at the documentation. Also look at our tutorials. Ask me questions. I'm an expert in R. I love answering questions about R programming, my favorite language. So what I wanted to do was to sort of come up with a hypothetical question and then ask Dave and Ahmed, like, how would you answer this question? If you were to sit down for PA, how would you answer it? So like this question was, it's the format is you're predicting, say you're predicting property prices. You have a bunch of apartments and you're looking at the features of the apartment, the size, the area, the quality, the number of bathrooms, and you're trying to predict the selling price. And so if this is a hypothetical question, it would say, using non-technical language, interpret the following variable importance output that came from a random forest model. Make recommendations for a property manager who wants to find the most profitable apartments to invest in. Write between 7 to 10 sentences. Now, you don't have to actually write 7 to 10 sentences, but I just want to hear your thoughts. If you were just given this question, how would you answer it? I want to hear from both Ahmed and Dave.
Well, to answer it, like the variable section, sale price per square feet is the most important variable, I guess, here, because it is in apartments are to be invested. So I think that's the most valuable variable which can affect the investment.
Yeah, so I think what you're alluding to is that this one is much more important than all the others. It's like twice as important.
Right. The graph shows.
Dave, how would you answer this?
Well, I couldn't hear most of Ahmed's answer, so I apologize if I'm repeating the same things he said, but sale price per square foot looks like it's a really important one. Before I would place too much emphasis on that, though, I would try to normalize some of these things so that, and I don't want to use the word normalize with the property manager, but beforehand, I want to normalize some of these things to get a better feel for what might be important if they were treated on equal footing there. And then based on that to go back and say, sale price per square foot was a big factor. Central air is a big factor. In this location, you're going to die if you don't have central air. But it might be that whether or not you have a full bath or whether or not you have a garage is very important. But those things would emerge as we start to do our analysis there. And ahead of time, I couldn't go on just the numbers there.
Yeah, so that's a perfect example of how you could have a really correct answer statistically, but it wouldn't answer the question in the prompt, because the question in the prompt said using non-technical language. And so I think a better answer would be like this. Like, our model identifies the key drivers of rental demand. The following graph shows the relative influence that each characteristic of the apartment has on the number of people who apply for it. So instead of looking at this, graph and trying to explain what percentage MAE increases for et cetera, that's really complicated. Just look at the ranking. And then, this automatically considers other factors. For example, if an apartment has a low sale price per square foot, it will have many applicants regardless of if it has air conditioning or not. When students need housing, the quality of the furnishings, such as the number of bathrooms, whether it has hardwood floors, carpeted floors, the type of garage, is not important because they only need the apartment temporarily. And then we recommend that you apply filters to the apartment listings to narrow down the candidate units. First, filter out apartments that have a sale price per square foot that's too high or too low. Then choose only apartments that have central air, built-in or attached garage, and then filter out apartments that are close to a university where students require seasonal housing. Another example. So here you see first the old format, and then I have a hypothetical new format question where it's going to ask you to do more writing within your tasks. So this was from, PA 12/7/2020, and it said, select an interaction to consider in your model. So explain what an interaction is. And then I've crossed out the actual question. I've added what I think will be a new question. Using non-technical language, describe why 3 possible interactions may be present in this data. So the way that, so everyone who's taken this, I hope you've worked on this practice exam. And what I would say was you could look at these two. First would be holiday and weekday. Weekdays have a high volume of pedestrian traffic with the exception of holidays. Retail stores are closed during holidays, and so foot traffic is greatly reduced. And then temp and wind speed. Think of wind chill. If wind chill depends on both the temperature and the wind speed, that's an interaction effect. There is less traffic when wind chill is high and more traffic when it is low. Our model can take this into account using an interaction effect. And you can do something similar for weather situation and hour. I don't want to turn this into a lecture. I just wanted to touch on that. This next part is really for you to help you put together all of this knowledge to see how it works together. So this is using something called a knowledge tree, which is a way of relating the info. Typically when you study, like you just read a textbook, you're just going to study things linearly from, read this chapter, then read this chapter, then this chapter. But really everything that you're doing is sequential. It's all connected. So like, this is a typical exam. Over here, you'd begin with a business problem, and then you'd either have to make some predictions or understand the data. So if you look at hospital readmissions or the bike sharing demand, those are examples of making predictions. If you look at the customer value, customer phone calls, the traffic safety exam, those are really about understanding the data. And then you want to try out different things. So when you answer your questions, they want to see that you're following the prompt, but you can also explain like what alternatives you could do. Like if they say, understand the data, you have different options. You could inspect the data. You could just ask questions about the data. You could form hypothesis, and you could train a really simple model. If they say, oh, inspect the data, well, you have different options. You could segment it into groups using k-means or hierarchical clustering. You could do a correlation analysis. You could use PCA, like Dave was saying, and so forth. So then once you get to training your models, you then have to explain your model. You can do this in a lot of different ways. You can use a log link function with the simple GLM. You could use decision tree rules. You could look at some example cases. You could talk about the interaction effects. And then to validate your model, you can, tie this back to your initial hypothesis. Does it improve, or does it prove or disprove your initial hypothesis? Can you explain it using non-technical language and tie it all back to the business problem? So what I want you to do is to, think about, and when you grade your exams, how they relate to each other, and ask yourself hypothetical questions. If I hadn't used a random forest here, what other model could I have used? So the other type of exam that you're going to see is when you're just making predictions. Like I said, bike sharing demand is a good example, or the health costs practice exam. So, if you're just making predictions, you're probably going to use a random forest, a GBM, or an elastic net. And then you want to look at, the variable importance and the partial dependence. If you're using elastic net, you need to decide, do I want to use ridge regression or lasso? And do I want to, or I could even use an average of the L1 and the L2 norms. And then once you choose your model, the validation step becomes really important because you want your predictions to work in real life. And so you want to be careful about how you choose performance metrics. Then use, if you're doing a regression problem, you have to set, if you're doing regression, you don't have to set the cutoff value. If you're doing classification, you have to set the cutoff value and then look at the confusion matrix. So the next part is just, we're just going to go through some questions. Well, actually, no, we're going to save this. We're going to save this because we do have time. We do have until 11. So I'm going to go actually ask Ahmed and Dave again. If you were to, add to this picture, like let's take, inspecting the data. What other methods could you use besides clustering, correlation, or PCA?
One thing that jumps out to me as having been left out that I think should be explained in a lot of answers is look for the availability of a subject matter expert, because the data by itself may be misleading. Actuaries are great at numbers, but we're not great at knowing all the intricacies of this data and what its purpose is. The subject matter expert can be a tremendous asset there.